In this lecture, we'll talk about independent events. So let's say that I have an experiment and I have two events which I call A and B. By independent events, we basically mean that these two events have nothing to do with each other. Let's say, for example, that I'm rolling two dice, one blue and one red, and A is the event that the blue dice shows a 6, while B is the event that the red dice shows a 6. Then those two would be independent events. Whatever happens to the blue dice will not affect what happens to the red one. We need a more formalized definition of independent events, and this is the technical definition. The events A and B are independent if the probability of the intersection, that is, the probability that they are both true, is equal to the product of these probabilities. Let's say that I flip a coin twice. In this case, I get tails in the first and heads in the second. In total, there are 4 possibilities. So the sample space is given by I could get heads in the first and heads in the second. I could get heads in the first and tails in the second. I could get tails in the first, heads in the second, or I could get tails in the first and the second. Those are the only 4 possibilities when I flip a coin twice. I assume that the coin is fair and therefore that each of these outcomes is equally likely. Let's consider two events. Event A is I get tails in the first coin flip, while event B is I get tails in the second flip. Now, what happens in the first flip really shouldn't affect what happened in the second one, so we would expect A and B to be independent events. And so let's check that they actually are independent by validating this formula. The event A is tails in the first, so it contains two outcomes, tail head and tail tail. Event B, tails in the second, contains two outcomes as well, head tail and tail tail. A intersection B, the event that both are true, well, that happens only if I get tails in both tosses. And so we see that the probability of A intersection B is 1 by 4, as A intersection B contains one outcome. Similarly, we see that P of A is 2 by 4, or 1/2, which is the same as P of B. And so A and B are indeed independent, as the product P of A times P of B is 1/2 times 1/2. That's precisely 1 by 4, and that's equal to the probability of the intersection. Here is a very important result. If I have two events A and B that are independent, then this conditional probability A given B is equal to the unconditional probability P of A. That makes sense. If A and B are independent, they have nothing to do with each other, then knowing B shouldn't affect the probability of A happening. So the probability of A would be the same if I condition on B or if I consider the unconditional probability. Going back to the example of flipping the coin twice, if I know that B is true, that I got tails on the second flip, that really tells me nothing about the probability of A. The probability of getting tails in the first coin toss is 50%, no matter if you got tails when you flip the coin the second time.